Thanks, everyone. Welcome to STEMcon. This is just a great event. I'm going to talk a little bit about what we do at College of DuPage in terms of meteorology, specifically severe weather. So the title of my talk here is a quick introduction to tornado prediction. And we are going to launch a weather balloon after this. So it's even though the weather's not the friendliest for us, it should be a lot of fun. I start off all my talks whenever I talk to anyone about severe weather. It always starts with this idea of sensationalism and the way that news is reported in our country. And one of the things I found here funny, right? If you take a look at the graphic on the screen, it says, the Titanic sunk 102 years ago tonight, and that was considered breaking news, right? Well, in our country with tornadoes, the way they are portrayed, we see a very similar thing, okay? How many of you have seen one of these movies listed up on the screen here? Right? Anybody seen any of these? Twister is probably the storm chaser favorite. Sharknado, Night of the Twisters. But what's really interesting about all of these movie covers, the tornadoes always look the same, don't they? They all look like a very slender elephant trunk type of tornado. They're very easy to see, okay? They're all doing damage that's very visible, and the way that we sort of portray tornadoes is this type of image. Unfortunately, when you get out into the field and you actually look at tornadoes, what you often see is stuff like this. This is the May 31st, 2013 El Reno tornado. This tornado unfortunately killed 3 storm chasers, 2 of which were actually researchers that were trying to drop instrument packages inside of the tornado, a very dangerous endeavor, okay? The Weather Channel was also out that day. This is a picture of their vehicle. They were out providing live coverage to people, telling them to get out of the way. And shortly before, they told everyone to get out of the way. They were driving south away from the tornado, and the tornado hit them and threw their vehicle a couple hundred yards into a wheat field, right? These tornadoes can be very dangerous and very destructive, even for people that understand how they think they understand how they operate, okay? So, just quickly, what is a tornado? How do we define a tornado scientifically, okay? All the bullet points are up there on the screen. The idea is these are very violently rotating columns of air. They're touching the ground. If they're not touching the ground, what do we call them? Anybody know? A funnel cloud, yes, absolutely. Most tornadoes are brief, thank goodness, lasting only a couple of minutes. Some of them can last for over an hour. In fact, the great infamous tri-state tornado of 1925 lasted almost 3 hours and covered 3 states. Pretty impressive. What we see in terms of where people are dying from tornadoes, about half of people that are killed by tornadoes are in mobile homes or weak frame housing structure. So we have a long way to go in terms of making those places safer and educating people that live in them. Tornado forecasting. Wow. We have come a long way since I've been alive, okay? It's incredible what we can do now forecasting tornadoes. This was a forecast for the tornado that hit Coal City in 2013. It also hit Washington, Illinois, and did very destructive damage downstate in Washington. This was a forecast on the day of the event. There was good warnings and watches for this event almost 8 days in advance leading up to where we thought tornadoes were going to happen. Look at the next slide. This is the actual reports that happened that day, okay? The red dots are tornadoes. So let me just flip back and forth there. The red dots are tornadoes, the blue dots are severe wind reports, and the green dots are hail. And you can see the forecasts for these types of big outbreaks are becoming better and better and better. As our technology gets better, our understanding of storms become better. We can now do a really good job of warning the public when these events are going to occur. Okay? This is an incredible image. Okay? This is looking down on the city of Joplin, Missouri, prior to the tornado event in May of 2011. Okay? You can see the high school very well, all of the residential neighborhood. This was before the tornado. Take a look what happened after the tornado went through. This is pretty incredible. Right? Extensive damage. In fact, this particular block experienced EF4 tornado damage which was actually not the most damaging part of the tornado, but still just an incredible image. Let me go back and play that one more time for you, before and then after. So the moral of the story here, right, is that these tornadoes they're extremely destructive, and many people that you survey and talk to after the tornado, that's a defining moment in their life. They talk about what happened before the tornado and what happened after the tornado, and it's an incredible milestone in their lives when these sort of events happen. And thankfully, for the people that actually lived through these events, the Joplin tornado killed 255 people, which is still a record since the tri-state tornado. So it's been an interesting week for me. If you've seen my face on TV, it's because we've gotten a lot of publicity about our new forecasting methods and our approaches to try to forecast tornadoes. The Chicago Tribune did a nice story on us. The headlines have been a little bit misleading, okay? They're trying to grab your attention and bring you in and read the article, like that sensationalism idea that we just talked about. But the science is there. We're pushing forward the frontier of tornado prediction in this 2 to 3 week time frame. We cannot pinpoint where tornadoes are going to occur 2 to 3 weeks in advance. That will never happen given our current observation network. It just won't happen. What we can do, though, is tell the public we are moving into a weather pattern or a weather regime that is going to be favorable for tornadoes or not so favorable for tornadoes. That's really what the science is about. It's something called angular momentum. Check this out. Oh, this was I was going across the bottom of the Fox News ticker on Saturday morning, a couple Saturday morning ago. This is kind of the reach that we've had in terms of our new method. Here's what the method is all about. We're detecting the jet stream pattern across the Pacific Ocean. Is it really stretched out east-west and very fast? Thunderstorms can actually occur in the Indian Ocean and Pacific Ocean that cause the jet stream to modulate into these big waves, which we call low angular momentum, okay, these big Rossby waves. So imagine somebody standing in the Pacific Ocean or the Indian Ocean with these workout ropes that is causing the waves to disperse downstream. And when we get these big waves, these roller coaster type of jet stream patterns in the United States, those are the ones that favor severe weather. So for an example here, if we had a big wavy pattern across the Pacific, the area shaded in red would very likely be the area that would experience severe weather based on what we can understand about tornado environments. Okay? Well, it just so happens, here's today's severe weather risk. In that very same red area, we are in very much one of these regimes of a big trough in the center portion of the country. We had a tornado report this morning from Louisiana, and you can see the blue boxes there on the image are the severe thunderstorm watches that are currently out, and there's actually an attendant tornado risk down there today. We have a team in the field right now. They are not chasing today because if you're familiar with this area of the country in terms of geography, there's a lot of trees and it's very hard to see anything. So they're going to stay out in the Great Plains and hopefully the storms will stay out of populated areas. I want to shift my attention really quickly to what we're going to about do here with this weather balloon launch. It's something in our field that we call numerical weather prediction. And so for all the young kids out there that like computers and like science, one of the biggest, most important things I can give you in terms of advice is to be comfortable with computers. If you like science and you like technology and engineering and math, computers are going to revolutionize the way we look at things in the future. You're already seeing this with IBM, the big data push. Numerical weather prediction is just that. We try to represent what is happening inside of a computer. Okay, this is extremely challenging. In order to do this, we have to have supercomputers. This is an example of what the supercomputer looks like. Inside of it, it has thousands of processors that are all talking together in parallel, trying to solve our equations for weather that are going to help us forecast into the future. This is really what impinges. This is why our forecasts are so good. I know there's people out there that probably think, oh, the weatherman's wrong 10 out of the 12 times, right? The truth is, if you look at the verification statistics, we are very good out to about 14 days. Extremely good. We can beat climatology out to about a month, and beyond that, we really start to lose skill. The only reason we can do that is because of numerical weather prediction. Okay? Let me give you an example of what this looks like. Numerical weather prediction This is an example of me in the field with our COD group. We launch a weather balloon into the field. It goes up through the atmosphere like those yellow arrows are showing you. Those yellow arrows, as the balloons ascend, are giving us the three-dimensional grid points that we need in order to initialize our weather models to forecast into the future. So it's all about these yellow arrows that are going up twice a day across the globe that are taking the measurements, putting all those measurements into our computer models, and then we're simulating forward into the future of what we think is going to happen. Okay? Here's where we take weather balloon observations around the world. Every one of those black dots is a location where we take a weather balloon measurement. And one thing you'll notice right away is there's not a lot of them over the oceans. Right? Not very many observations over the oceans. Because of that data void area over the oceans, we have to do a lot of interpolation, which really introduces air into our forecasts. So it's really that we're sort of guessing what's happening many times over the ocean or using satellite to supplement what we know. But over the land, we do a pretty good job measuring the atmosphere. In the United States, we measure weather balloons twice a day at every one of those white dots. We have one in Illinois, and the closest one to us is actually out in the Quad Cities, the Davenport National Weather Service office. We do not have one in Chicago. So here on campus, when we launch, we actually supplement the network because we don't have any observations in the upper air, at least over Chicago. Once we take all of that information, we feed it into our computer models, and this is what they provide. A beautiful animation of jet stream level winds. And the only reason that we can do this is because we launch weather balloons. If we did not launch weather balloons, our forecast would be terrible, awful. We wouldn't know what's happening, let alone tomorrow, 2 or 3 days from now, forget about it. It's these weather balloons that take the information, temperature, pressure, wind speed, dew point. We put them into basically a set of equations, and they forecast forward in time for us using Taylor expansion, high-level mathematics, to be able to provide us these sort of estimates of where things are going to be. We know there's going to be air, and anybody who looks at numerical weather models understands the caveats. Many people understand the caveats associated with these. This is the only reason that you can do this, because of the weather balloon network. Here's another example. We knew it was going to rain today. Here's a forecast from last night of the radar reflectivity throughout today. Big, right? You can see the rain shield move right over northeast Illinois. And thankfully, if you look at the timing of this weather model, it appears we're going to be clear here in a couple hours for the balloon launch. I take that back, 15 minutes. So we're probably not going to be clear. But it'll be close. It'll definitely be clearing up as we go on into the evening. And we can see that from our latest round of numerical weather prediction. This is the kind of stuff that we can do because we have very high-level computers. We can't do this without computers. It would take everybody in this gymnasium, okay, with a calculator and a pencil, sitting down, and we would be here for years just to figure out what's going to happen tomorrow. Okay, these computers can do this instantaneously. That's what's really important about supercomputing. Most of what I do outside of the classroom is in the field, and that's exactly what you're going to see here in a few minutes. Launching weather balloons. We take students out into the field. We get up close to thunderstorms, not inside of them, hopefully, get close to them. We launch weather balloons, and then those weather balloons tell us really what's happening in the atmosphere. And we can get a much better sense of where we need to reposition if we're storm chasing, if we need to get out of the way, sort of what to expect on any given day. And again, the only reason we can do this is because we have weather balloons. So these storm chasing trips are actually very educational in terms of we teach you how to forecast in the morning, and then throughout the day we're constantly watching how storms are going to evolve. And hopefully, if everything works perfectly, we get to see stuff like this. Okay, this is fine with me. This is a beautiful non-tornadic supercell. In this case, the weather balloon for this is actually, the data's in the upper middle corner. We launched this weather balloon, and about 2 hours later, we knew that the atmosphere was going to be extremely favorable for these types of storms, and we got close to one of these storms. And I can teach you, let me tell you, I can teach you more in the field. This is one thing scientists have to remember, right? We love to sit in our cubicles, we love to do what we do, but it's the field work, right? Getting out in the field and experiencing what you're studying, that's extremely important. And I want to make that point. The field, I can teach you more in the field in 30 minutes to an hour than I can all semester in a textbook. And that's the really important thing about field research. So what's cool, we've been doing this for a really long time. Before I was even here at College of DuPage, Paul Cervaka was doing this in the late 1980s. I hope that wasn't our weather balloon. And we still continue this year. Again, we have a trip out in the field, and we have 4 more coming up. You can track these guys in the field, so if you want to know what's going on, you want to see the pictures that they take, you can go to our homepage and check out weather.cod.edu/chasing/tracker. And our team is in the field right now. They're down in Texas, and it looks like they're going to be in Texas for the next few days, chasing along the Rio Grande, actually, so very far south in Texas. We also have a really excellent website if you're interested in accessing weather information, including those numerical weather models that I discussed. Head on over to weather.cod.edu, and you can get really anything that you're looking for in terms of weather data. It's all there, and it's free. It's open source, so you don't have to pay or anything to access this information. It's all there for you, okay? So, you guys ready to launch a weather balloon? Yeah? All right. So, before we do, I just want to talk a little bit about this balloon and what it does and where it's going to go, maybe. The winds outside today are pretty incredible. We're not really sure where this thing is going to land. The first thing that we're using, take a look up here on the slide, is the Intermet 1AXBN radiosonde. This is going to take temperature measurements, dew point, so humidity, pressure measurements, wind speed, and direction. It has a GPS sensor in it and a small 9-volt battery for power. It's going to communicate back to us on a radio frequency. So just like you use radio communications or cellular communications, this thing is going to radio back to us information on all these variables as it ascends through the atmosphere. We expect today that the balloon will probably pop somewhere around 10 miles above the surface of the Earth. Here's the balloon that's going to take up the package. It's a 200-gram latex weather balloon. Right now we have it filled up, if you look behind you, over at our weather booth. The fill diameter is about 5.5 feet. And when it pops at the top of the troposphere, which is the first layer of the atmosphere, it will be about 12 feet in diameter. Because of the decrease in pressure, the volume of the balloon will expand. We fill it up with helium for safety, because hydrogen would be fairly dangerous. And again, we're probably going to be talking about a 10-mile above the surface before it pops. It'll come back down on a parachute, and it might land, who knows where, we'll see. Last time we launched one of these weather balloons, it landed 2 miles from campus, and we got the weather balloon back. This one might land in Lake Michigan, so we'll see. We communicate to the balloon with this very sophisticated antenna. It operates again on the 400, we're going to operate today on the 404 megahertz frequency, and it sends power over the computer. So we'll be able to tell in real time as the balloon is going up exactly what all these measurements are. We're not going to have to wait until it pops and comes back down. So we'll know that information basically immediately. Okay? So we're going to launch. Here's what we're going to do for the launch. I'm going to walk over and grab the balloon. I have to attend to the computer really quickly to make sure everything's all set up. Our antenna is already outside, and then when I sort of give everybody the thumbs up, we're going to walk out the balloon quickly. It's raining outside still. We're going to let it go. We'll count down from 10 really quickly because it's raining. We'll let the balloon go, and then we'll come back in, and we'll have all the data from the weather balloon over at our booth. So if you'd like to see the data as it goes up, you'll be able to check it out. Okay? Sound good? Who's excited? We ready to go? All right, let's do this. Walk it straight out to the back. All right, give me a countdown, quick. 10,